Good day and welcome to the Sustainable Materials Management Webinar Series, a joint effort between the National Recycling Coalition and the Pennsylvania Recycling Market Center. My name is Wayne Bowen. I'm the Program Manager for the Recycling Market Center and will serve as your moderator today. Before we get started, we'd like to extend a special thanks to Bob Hollis of the Mobius Network for providing the webinar management software for this series, and Savannah Batowski of the National Recycling Coalition for assisting the RMC with webinar promotion and technical support. Today's webinar will discuss heat recovery from composting and anaerobic digester facility operations. Following the presentations, we will conduct a question and answer session. If you have a question or comment, please use the GoToWebinar dialog box located in the control panel on your screen. You may also use the dialog box to request assistance if you're experiencing technical difficulties during the webinar. Please note that an edited version of this webinar will be made available for viewing via YouTube links on both the National Recycling Coalition and Pennsylvania Recycling Market Center websites. The presentation slides from both presenters will also be made available as handouts you can upload them items on your webinar control panel. And now I'd like to introduce our presenters. We have Brett Reinford, who is manager of Reinford Farms located in Mifflintown, Pennsylvania, and Brian Jerose, who's the founder and president of Agrilab Technologies, LLC in Vermont. And due to time constraints, I'm not going to read the full bios, but they are available as handouts. So we're going to start off with Brett, and I'm handing the program off to you.
Thank you, Wayne. Well, hello, everyone. As Wayne said, my name is Brett Reinford. I am the office manager here at Reinford Farms. I gave myself that title. I do a whole lot of other things here on the farm. I don't spend actually that much time in the office, but I do take care of a lot of the bookwork, the HR stuff here on our farm. So I just wanted to kind of start this presentation by kind of talking about our farm as a whole. The heat recovery for our farm was actually completely unintentional. I'll explain a little bit more about that later in my presentation here. But we built a digester, not for heat, and so I'll talk about that here. So our farm here is located in central Pennsylvania. I know some of you folks that are listening in aren't from Pennsylvania, so we're right in the middle of Pennsylvania, close to Harrisburg, the state capital. The farm's owned by my mom and dad and managed by my dad, as well as my older brother, myself, and my younger brother. We have 17 full-time employees, and we have 3 additional part-time employees. Sometimes we feel like we need more. We certainly keep busy here on our farm. My whole family, my sister as well works on the farm. So there's 6 of us from my family that are part of this farm here. We farm 1,200 acres, mostly corn. We no-till all of our crops, meaning that we don't own a piece of tillage equipment. We don't own a plow or a chisel plow or a disc. Everything is planted and the soil is undisturbed. We have about 720 cows and milk about 650 cows in our parlor 3 times a day. And then we have another farm that we rent 4 miles down the road that my brother owns, and he raises all of our young animals. A little bit of the history of our farm. So we moved from Montgomery County, Pennsylvania. That's close to Philadelphia, Pennsylvania. We were kind of pushed out by urban sprawl. My dad wanted to keep farming. His family members did not. So we bought a little farm out here in central Pennsylvania. Started with 57 cows. It's all my dad owned, and a tractor and a plow. That's no joke. So we've been kind of growing the farm ever since. In 1998 is when we made our first big expansion, and that was from 110 or 120 cows to 300 cows. And then we installed a rotary parlor, which is a parlor that goes around in a circle as the cows get on and off. In 2008 is when we decided to invest in a methane digester, which I'll talk a little bit more about here. And then currently we're expanding our herd, hoping to get to maybe 1,000 cows as market demand permits. And then we're also building a second digester here, hopefully in the spring of next year. So I want to talk about how we actually came to the decision to buy or to purchase a digester. That kind of started with me, I guess, back in 2006 when I was finishing up my sophomore year in college. My one biology professor encouraged me to think of ways to be more sustainable, and that's always been something that's been of interest to me. And so I did a lot of research on different renewable energy sources, looking at wind, solar, and then wasn't too interested, but we looked at a methane digester as well. And we ended up deciding on going with a digester simply because of the aspect that a digester, after manure goes through the digestion process, much of the odor is killed. And I guess I need to explain for some of you that don't know what a digester is. It's basically a big mechanical stomach, I guess. You put food into it, and it has bacteria in it that eats the organic matter that creates a gas called methane, and that methane is extremely valuable to us on our farm. And so so we went with a digester that for the only reason basically was to reduce odor. We live in a pretty rural area here in Pennsylvania, but we had some neighbor complaints about all the manure that we spread. So we wanted to look at a way to kind of help our public relations here in our community. And so, and then of course the side benefit that we kind of knew of was the electricity, but that you can produce with them through the use of the methane that you capture. And that wasn't of much interest to us because at the time it didn't really pay for much of the cost, and actually it still doesn't really either, even though we produce quite a bit of electricity. So anyway, it was a 2-year process. So from 2006, when I said, hey, let's maybe go with a digester, to doing all the permitting, to getting the grant funding, we built the digester. Then it was up and running in 2008. So basically what we want was the brand name, is an RCM complete mixed digester. It's now owned by another company called Martin's Energy. And again, we started in 2008, and then we sized it for 1,000 cows back in 2008 because that was the plan, to grow quickly to 1,000 cows. We haven't got close to that number yet, but thank goodness we did, for another reason I'll talk about here later. And so it produces 140 kWs an hour of electricity, which is enough to power our farm and about 80 houses here in the community. We flare a bunch of excess gas because our motor isn't big enough to handle all the methane that we're producing now. And then we also separate the solid manure from the liquid manure, and I'll show you how we use that here. It was a $1 million project. 60% of it was financed by grants, and then it doesn't require that much time a day, maybe 15 minutes a day when it's working right. And so I'll explain to you what's going on with our digester here in a bit, and in regards to heat as well. So what we put in our digester to make heat is manure from about 700 cows that are here on our farm. We scrape the manure 3 times a day, and then it's pumped into our digester every 4 hours. A little bit's pumped in every 4 hours. And so our farm, with all the cows that we have and that we capture, and all the manure that we capture, it's about 12,000 gallons of manure a day. So manure is where we get some of our methane from, and then we also put in food waste. So here for the last, since 2008, basically we've been getting food waste from somebody. It's come and gone in spurts. Here recently in June of this year, we decided to invest in a food waste depackager, and so we've been getting beer, cans, lots of different grocery store waste. So anything in packaging, it's kind of helped us have a more consistent food, I guess, for our digester, help us more consistently produce gas that eventually makes heat. So so we started doing this here in June, and this has kept us pretty busy. Just down in the bottom left-hand corner, it's a picture of our packager building that helps us keep all the food waste that companies are trusting us to destroy, lock down, and secure. And then the other two pictures is kind of the machine that we use and some of the cardboard that we recycled. But yeah, so that's so food waste is a big item that we put into our digester. We get about 30 to 50 tons a day on any given day. It depends. Some days we'll get 0, and then some days we might get 75. So I say 30 to 50 tons a day is what we get. So we put it into our digester, and then we have a second one that my brother owns 4 miles down the road that he also gets some food waste as well, and that's where our young cows are at. So before I talk about heat, I'll talk about some of the things that a digester produces. So on our farm, again, it produces electricity enough for about 80 houses in our farm, and we sell that to our local power company, PP&L, and they pay us once a year for any excess that we have. And to be honest, you know, we're getting to the point as we add more barn fans and more just more motors, electric motors. We're getting to the point where most of the electricity, we're not there yet. Some of the electricity is, well, there's very little that we sell excess, but we still think we have enough to power 80 homes. So there is some being generated, but in the next few years, if we continue to grow and not add another motor, we'll just be using all of our energy on farm. Another thing and so that produces income for us. And so then another thing that we get out of our digester is bedding. So I talked about the separator a little earlier that separates all the solids from the liquid. We use the solids as bedding. It's completely sterile since it's been in the digester at 100 degrees for approximately 30 days. And so the cows love it. It's nice and fluffy. And so that saves us, by using just recycling manure, essentially, it saves us about $50,000 a year, and it's a really healthy, comfortable product for the cows to lay on. But so I know you guys are all here to hear about the heat, so I want to talk about that for a little while here, and especially how we use heat on our farm. So this is a picture of our farm, kind of a bird's eye view of our current operation, taken probably about a month or so ago. And I'll be referring to this picture quite a bit, just simply showing you where we have lines run all over our farm. Normally when I talk about the heat that we have on our farm, I'm giving an on-site tour, and so it's easy to point out things and people can follow along, but I'm afraid you get lost if I was just talking about it. So we're gonna kind of go on a little tour here of our farm. And so waste heat. So we have a lot of waste heat, and it's I guess I shouldn't say that it's waste because we capture most of it. So basically, what happens is we're producing a lot of methane, and that methane is pumped into this yellow motor here that's in front of you, and this is where the electricity is made. And this motor produces a lot of extra heat. Some of it's coming from the actual motor running, like the coolant, the water that's inside of it, and then quite a bit of it is coming from the exhaust. And so if you look on the screen here on the left side, that picture, you'll see like a vertical silver cylinder, and that is where we actually capture the heat off the exhaust. So well, I guess I should lead into this. So our motor is actually not running right now. We just kind of blew it up here on Saturday. And we're not sure what happened. We just had it rebuilt a month ago. So something went wrong. And so it's actually not running right now, but I was fortunate enough to get some numbers as far as heat before that happened. So when this motor is running, it's producing about 550 Fahrenheit temperature of heat coming off the exhaust, not the motor, but off the exhaust. So that exhaust is running directly into that silver vertical tube there, and we capture a lot of heat from just the exhaust pipe. And so you see the piping there. It's kind of confusing, but in there we have several different circulator pumps that are pumping that hot water. So we do cool it down a little bit because it would be steaming, I guess. So we have a not heat exchanger, but that blue thing there, it kind of helps cool down the water a little bit so that we can pump it to various parts on our farm. So we capture the exhaust. It's 550 degrees off exhaust heat, and then the motor, of course, is running at about 180 degrees constantly, and so we're circulating water through that. That's also going out to various spots on our farm. So this is where all the heat is captured. This is where all the heat is made, right here on our farm, and now I'll kind of go through where it all goes and how we get it there. And it's pretty cost effective in getting the heat where we need it to go on our farm. So if you look at this picture, when I talk about the digester motor, I have a little green box there. That's where the digester motor is located, just to the left of our front of our barn, which is our milking facility. So we have it there. The actual digester is directly to the top. It's out at the other end of the barn there. I put a blue and red arrow there for you to kind of show. So the first place that all of our heat goes to is the actual digester, where the gas is being made. So that needs to be at a constant temperature at 100 degrees always. And so that tank is insulated. There's 450,000 gallons of manure and food waste that are in there for 20 to 30 days. And so we're always adding, so if we're adding 12,000 gallons of manure a day and 12,000 gallons of food waste a day, we have to heat that to 100 degrees pretty quickly. And so there's quite a bit of heat that goes into keeping that tank warm at the right temperature, so that the bacteria and the methane producing bugs are not dying off. And so that's where we direct all of our heat, primarily if there's an issue with like the motor or something. So we keep that warm. That's how we keep the digester alive. The other place that we use, so the other place that waste heat goes to is our pasteurizer. And so this is located directly to the right of the digester motor, just on the other side of the wall. And so we pasteurize all of our milk with the free heat coming off that motor. It makes the milk way healthier for our calves. We get way healthier calves. And this is just a pasteurizer that we built ourselves, put some heat pipes inside of it, inside an old bulk tank, and have some valves on it that we run hot water through and cold water through. And so we're trying to heat the milk to 140 degrees for 30 minutes, and we have to do that pretty quickly. And so this motor does that no problem for us. So we get it up to 140 degrees for 30 minutes, and then we cool it down to about 85 degrees or 90 degrees with some cold water that we flush through it then as well. So we use heat for our pasteurizer as well, and that saves us a bunch of money. If we were to buy something like this brand new, we'd probably be at $8,000 or $9,000, and it would be like an electric heating system or propane or something. But for us, it's just an old cheap bulk tank and some pipes, and it does the job for us. This is this slide here is kind of referring to where we get our heat from for the milking parlor hot water, and for our house hot water, and for our shop hot water. And the next slide will kind of show you where this is located on the farm. But so we bring all the heat from that digester motor over to, well, I'll just show you. So we bring all the heat over from the digester motor to our heat exchanger located at another part on the other side of the barn, I guess. And so we bring it there. It comes in at about 200 degrees or around 108 degrees. And we run it through these heat exchangers that are located on this picture here on the right side. And from there, we divert the heat to 3 different places. We divert it first to the hot water in the barn. We use a lot of hot water when we wash our and sanitize our milking facilities. So that happens 3 times a day, and typically we're using anywhere from 200, 300 gallons of hot water 3 times a day. So, up to 1,000 gallons potentially a day of hot water that we have to heat to. We heat it to 180 degrees. And so had we been buying fuel oil for that, that would be pretty expensive for us. So typically when we were doing this was 10 years ago that we actually had a fuel tank there that we were using fuel oil with. It was around 250 gallons a month. And so right now that's a savings for us at about $600 a month in fuel oil that we don't have to purchase anymore just to heat our hot water in the barn. And so that's a saving for us. And then we have the another circulator there on the left side, that's a little green thing that sends hot water to our house, I'll talk about later, and then hot water to our shop as well. So this is where all the water gets kind of diverted. So we bring all the hot water from our digester motor into this area via an 1.5 inch, no, sorry, they're 2-inch pipes, just regular black steel pipes, and they're insulated. And it's about 100 feet from here to the motor, and so we would pump it through the rafters over to this area. And then from there, the circulators are tied into some PEX piping that goes to our shop and to our house. So again, this is just the picture showing where we send that hot water over to our heat exchanger in the room. And also in this room is where we have employee lockers and everything else. And so in the winter, that stays nice and warm. All the hot air coming off all the hot air coming off those pipes keep that room nice and toasty. We also use hot water for our house, or for my parents' farmhouse. They have a backup oil furnace in that house just in case. And so actually today it's being used simply because we need hot water for the barn. And so they're using that. So we're sending hot water over to there at about 180 degrees to this house from that heat exchanger through PEX piping that's located under the ground. And it's insulated PEX piping, so we don't lose the heat on the way over to the house. And that keeps that house plenty warm in the winter. And again, it's all free heat from our motor that we're using. Kind of funny thing that happened yesterday, we called for fuel oil because we need to order some, and they called me back and said, "Are you sure we're sending it to the right address? Because we haven't delivered any fuel oil to this location since the beginning of 2015. And I had to chuckle because, we haven't bought fuel oil forever on our facility here. So you can see the pipes kind of just go under the ground there over to the house. And then the last place that we send hot water to is our farm shop. And it's a pretty big building. It's about 70 feet wide, I believe. 60 feet wide and about 110 feet long. We have radiant heat inside the floor, and this place stays plenty toasty as well in the winter as well. We just have a bunch of excess heat that we can send over here, and it kind of helps with employee morale and keeping people warm in the winter. And so just the picture on the right kind of shows our radiant heat. We just put this in a backup furnace in this location as well, and I believe we're using it today as well, just to kind of keep the digester warm and also make hot water for us. But this is another location that we have a backup furnace that rarely gets used. And then you can see on this screen here, it's the red and blue arrows on the top right is kind of where our shop is located over there. So all that's under the ground as well. So that's where we send hot water through our farm, mostly under the ground. And then we also have access to heat that's in the digester motor room. So when we close the doors where the digester motor is, it'll get to 90 degrees inside there if we don't turn any fans on to vent it. And so what we decided to do in the winter is we put a fan in the ceiling with some little air duct piping. And what we do is we suck the air from the top of that room and blow it over here into our parlor. We have 2 milking parlors, one for milking cows and others for our cows that we give the milk to their calves. And so we heat both of those with the hot air that's just generated inside the motor room in the winter. So again, free heat, and it's right next door to the motor, so it's easy to get it there. And then the other, and probably the biggest savings that this digester produces for us is the ability to dry our own grain on our farm. And so we pool all the hot air. We'll start drying corn here probably 2 days once our motor's up and running again. We'll put a cap on top of that picture on the left. We just kind of build a box around the radiator, and there's a 30-inch pipe buried under the ground that goes to these bins here on the right. That's probably about 20 yards away. And so we suck the air off of that and blow it into our drying bin. And the temperature, we can control the temperature of the heat just by opening and closing the pipe valve that we have built into it. And we dry our own corn. So this year we'll do we'll do about 75,000 bushel of corn and dry it all, and that'll save us right around $20,000 on drying costs. And again, that's just free heat that normally is just vented to the outside air, but we've decided to capture it and use it as a way to make our farm a little bit more profitable. And so this picture here just kind of shows where we put hot air. So the hot air on the left, the arrow on the left, the hot air is just kind of blowing it into our drain grind bin, and then the hot air, the other arrows is just showing that where we put it into our milking parlor. So this is how we use all the heat on our digester right now. In the summer, we have plenty of extra heat because we're not heating the house, we're not heating drying grain or anything. And so we're always looking for ways to figure out what to do with it because it's free and it's being wasted, I guess, right now. We are building another digester here, just working on the permitting stuff right now. So hopefully in March we'll be breaking ground. And along with that will be another motor that's about 4 times the size, which is going to equal more heat. I don't know if it'll be 4 times more heat, but it'll definitely be at least as much as we're getting now. And to be honest, we don't have any use for that heat yet, except for our depacture building up there in the top left-hand part of the screen. We're going to heat that building with that motor, but then all the hot water that we will have extra. We have plenty of ideas. I'm just not sure which one we're going to choose yet as far as how we're going to use it. A couple years ago, I tried to use the excess heat off the muffler that's buried under the ground on our current motor, and I built this greenhouse right on top of it, and it blew down as soon as I had it up. So I lost my motivation to continue on with that, but I was planning on doing maybe aquaponics or hydroponics in there and have a greenhouse year long. So that's an idea for us, but we have local businesses that do use hot water, and there's some ideas, or we're toying with the idea of just heating a tank and a trailer, an insulated trailer, and then delivering hot water to them as they need it. But yeah, so there's lots of possibilities for heat. If you have any ideas for us, let us know. Most of the ideas that we use on our farm actually have been given to us by other folks, but when we built our digester, we had no idea that we could use all this extra heat, and there's plenty of extra in the summer that we can use, and with this second digester coming online, we'll have plenty of others. Unfortunately, we're not close to any businesses where we can pipe the heat under the ground over to them in a cost-effective way, but we're always trying to think of ideas. But anyway, so just thank you for being a part of this webinar, and there's my contact information. If any of you want to reach out to me later on, feel free to do so. My phone number is there, and also my email. But yeah, that wraps it up for me. Wayne, if you want to take it back, I appreciate it.
Okay, Brett, thanks. So we're going to switch screens here, so bear with us for a minute. While I'm doing that, Brett, could you tell us how much gas you produce? I think the question was how much SCFM?
Yes. All right, so that's a good question. I knew somebody was going to ask that, and we have a gauge on our motor, and before it shut down here, it was running. The gas going into our motor was 52 CFM. I don't know if that makes any sense to you, that number. And then we also have a flare that was taking about, I think, another 25 CFM on top of that. So I don't know, 75 CFM is typically, not typically, but it's what we're producing right now. But yeah, that number obviously changes depending on our feedstock. But yeah, if that helps answer your question.
Yep. Okay. Thank you. All right. Okay, Brian's screen is up, so I'm going to introduce Brian Jerose, President of Agrilab Technologies.
Good afternoon. My name is Brian Jerose, and I'm President of Agrilab Technologies. Thanks for listening on to this webinar today through the Pennsylvania Recycling Market Center. The presentation is focused on our work that we do with aerated composting with renewable thermal energy systems. The little quick background on our company. While I've been working in this field for around 20 years, we've collaborated with a company out of Canada, Agrilab Limited, who did a lot of industrial and still does a lot of precision heat transfer applications in industry and aerospace. They had a division, Agrilab Technologies, that focused on heat transfer in agricultural settings. After partnering with them on a project in northern Vermont, they helped get us set up with a Vermont-based company, Agrilab Technologies, and we've now since been designing and marketing and installing and servicing integrated compost aeration and heat recovery systems. We still do a fair amount of consulting and technical contracting work. We've gotten work on that level as far and wide as Delaware and Michigan, but we've specifically installed these systems now in 5 states in the Northeast. Vermont, New York, New Hampshire, Massachusetts, and Connecticut was our newest one this summer. And we've got a unit that we sold to Wales, and that should be coming online in the coming weeks. This next slide here is an overview diagram of how this process works. In the center of the slide would be a typical one of our units. Those are the mechanical components, the aeration fan or blower, the specialized heat recovery equipment that we've developed, number of other features related to plumbing, circulating water, or heated glycol to different end uses, and the various sensors and controls. So that's at the center of here, and we offer that in a skid package, in a cargo trailer, and in 20-foot shipping containers. Our earlier systems were all built on farm sites. So we place this wherever it makes sense on the site, and we aerate compost, meaning that we force or draw air, primarily draw in the negative aeration mode, the hot vapor out of compost piles. For the compost process, that works to oxygenate and accelerate the decomposition process in a managed fashion. But importantly, by drawing it through negative aeration, we're essentially sucking that vapor into our system, we're able to recover that heat. So that's what we do uniquely, and we're able to apply that to a number of applications. Again, our first sites were all on farms. Sometimes that was for heating floors, for wash water, greenhouses, and other farm uses. And now that we're getting into more commercial and municipal projects, product drying is one of the uses that we use that recovered energy for. The vapor that goes through the system is either exhausted to the outside air, or if they're in a location that's more sensitive for neighbors or an urban developed area, we can then direct that slightly cooled vapor into a biofilter and also have some odor control benefits. A couple of the projects that we wanted to share, particularly in this webinar, are some customers and projects that we've done over the last year or so. The one here, the Foster Brothers Farm, also are the operators of Vermont Natural Ag Products. They're the largest compost site in the state of Vermont, and they've been going for 25 years and have developed a bagged and bulk line of products that they sell into a number of northeastern states. Here's a shot of their picture, an aerial photo from the south looking north. In the far background is the existing dairy, but in the foreground, primarily what we're looking at is their composting operation on a 10-acre site. They have stormwater ponds that you can see here. The runoff is controlled and conveyed into that, so there's no discharge off-site. They are blessed with 1,000+ acres of cropland, so that they're able to use the recovered stormwater for application onto their crop, hay, and other fields to irrigate and to manage the nutrients and sediment in that material. Historically, they've been exclusively a turned windrow operation, meaning that they use payloaders and other specialized mechanical turning equipment to mix and then turn to blend and bring air into their piles to accelerate the decomposition process. The next few slides I'll go through a little more quickly, but essentially this was the process for how we converted a portion of their site into an aerated static pile system that also has some turning involved as well. So right here we're looking at the northern portion of the pad, and they put up a hoop structure for some of the windrows that they wanted to control precipitation but the bulk of their windrows, both aerated and non-air and just still mechanically turned, are out in the open. So what we're doing here is a combination of the pipes are on grade or above, pipes on grade, or basically the pipes are sitting on top of the working pad for the aerated portion under the windrows. To connect them to our fan and the other mechanicals and heat recovery equipment, the pipes did go underground to permit equipment access around the site without having to drive over pipes. Here, this was the header pipe, and this lines up to where we were going to place the box. In the background, that green building is where the Fosters bag and palletize their products, and you can see a few of those wrapped pallets out in the yard as well. But that bagging building shown is one of the energy loads that we were able to meet by recovering energy from the composting process to heat the radiant floor in that building. Here's a picture of Ryan Kolosky and our team doing the fusion welding of the aeration pipe. We have on earlier projects used PVC pipe, and that's still somewhat common for some aeration systems. This DR17 pipe is made of high density polyethylene, just far more rugged and durable. And you can either perforate the aeration holes yourself or can come through the manufacturer. After welding and lining up all the pipes, they came out to our landing pad. Again, this is where at the edge of the site where our unit will sit. And basically in this 20-foot shipping container that is shown right here, it shows up and it's plug and play, so to speak, ready to be connected. So these next few slides illustrate we make the quick connections using flexible or ideally rigid pipe to catch the stubs of the aeration channels to those metal intake ports on the back of the unit. So that's where we draw the air and the heated vapor into the system and are able to aerate the piles. In this picture, this is inside of our shipping container, the hot box. This is the blue and red pipes coming up through the floor are how we circulate the hot water and return to the bagging building to provide that heat. The next slide here is in their bagging building. This is where they already had an existing boiler, so we were able to loop into this system as a primary source of heat. And then in the coldest days of winter, and yes, it does get to 20 below at times in Vermont, their boiler's still on hand to be able to kick on and provide the necessary heat. In the winter with that garage overhead door, the forklifts carrying pallets of product in and out can cool off the building a number of times during the day. So there is a significant load to heat that building and maintain it at a comfortable working condition. Electricians here, again, they were probably only half a day to plug into how our unit was wired and bring service from the existing panel on the site. And after everything's connected, you can see on the right of the screen, our shipping container, the hot box in the foreground, and then looking back, the pipes go underground and then resurface under the coverall structure. So you should be able to see the black pipes that come out, and two lines end up going under each windrow in this portion of the site. Little closer view of the pipes under cover here. We did end up bringing them closer together, but first they were laid out trying to match the 18 or so foot width of the windrow that they use. As part of the aeration process, we want to be able to distribute air evenly at the base of the pile. So putting the coarse, clean wood chips up around and above the pipes it accomplishes that better air distribution at the base of the pile, the part of the pile that in a typical turn windrow would be most prone to running out of oxygen and slowing down the decomposition process. Here's a view of the wood chips fully placed. And then here's a shot of one of the pipe arrays being covered with raw feedstocks to get the composting process started, next to another array of pipes that are ready to be loaded. I like this picture just because it shows that these small aeration holes on the underside of the aeration pipes are capable of not only pulling in enough air through the material to bring oxygen into the core of the pile, but they're also capable of drawing in that hot vapor that then runs from some of these channels 100 or more feet into the unit, and we're able to recover temperatures as high as into the 160s. So this is fairly standard using resources like the on-farm composting handbook, and there's other engineering methods to get the right perforation schedule, but that's something that we've been able to refine over the years on these projects. There is some loader work in the process as well. There's Jim Foster, one of the primary site manager, loading materials on top of some of the outside aeration zones. And here's a picture for those of you who may not have seen these before. This is called a straddle turner, essentially a mechanical tiller that goes over the pile and is able to mix and blend and at least for a short period aerate the materials in a compost pile. This picture shows as the turner is passing through the material, but I do also want to point out that plume of steam. That is common anytime people have seen that in a relatively cool day or even not. There's so much energy and heat within these piles that steam is indicative of how much energy is being released. So while that still happens to some degree during these turning events, that's really the source of energy that in these projects we're pulling into the ductwork and then over the specialized heat exchanger, and that's the renewable energy resource that we're putting to work on these projects. This view is looking back from the compost piles towards the aeration unit. Again, the pipes travel underground for some period. The white wrap is insulation around the ductwork as it goes into the intake ports. Above that, to the right, the other circle is the exhaust port. So when we're running exhaust, you can often still see a plume of steam coming out. And on the left, the hood with the orange tape is intake hood, for which is the air that we heat up to push into drying zones when we're looking to dry finished product prior to screening or bagging or other materials like bedding that they've dried using the energy from the system. This is a view inside of our hot box, the 20-foot shipping container that has the mechanicals. So it shows our blower, the different ways we have valves to isolate and control which zone of compost we're pulling from, shows some of the circulator pumps and plumbing for how we circulate the hot water or glycol mix to heat the building or to go heat the drying loop for drying product. In the foreground is the control panel. The operator on site can use a series of touch screens to track the different temperature trends for different zones, change settings for the fan speed, the timing for how long each zone gets aeration. And one of the big advantages for us recently is that this is something that we can, on our team, view and control remotely. So depending on the operator relationship that we have, we can set up and monitor and control those systems ourselves, or at least provide feedback and guidance when the operator is doing new batches or would like to do troubleshooting. Jason McCune-Sanders, one of our lead engineer on our team, at the front of the unit, and you can see for scale the different mechanical components in there and a small workstation that we have. Another closer up view The one thing that I can point out in this slide is the top bank of valves and pipes is a recirculation plenum. So that allows us to push heated or dried air back out into any of those zones. And that's another way that we can accelerate the process during the active phase or push the heated dry air into the compost piles when we're at that phase of the process. Here's a screenshot of the control panel. Again, it's a dashboard showing the different temperatures and flows, both of the vapor, but also on the water side, and shows which zones are open, which pumps or fans are on. So this is the interface that we have to work with. These other screens can also help us change the settings on the timer, and the aeration and water trends can show us how much energy and how much, what the temperatures are for vapor and water when we're aerating different batches of compost. Here's an example of the aeration graphs. You can see how temperatures typically increase when you've got a batch of compost going in aeration mode, and it'll climb up, and we can adjust the controls based on the trend of the temperature. Obviously, we don't want to overcool the piles, so it's important for us to keep track of maintaining good conditions in the compost first, and then efficient energy recovery is a natural outgrowth of that optimization. So going into this project, we are working with, again, the Foster brothers, who are experienced composters for a number of years. So they went in with these expectations that given the length of the runs, we'd probably only get 140 degrees into the system, partially replace their fuel oil, reduce their compost processing time by about 20%, and a few other expectations on managing it. The drying of again, the more of the assumptions, they wanted to get away from using their propane dryer as much or completely. They use that for some of their product lines, again, so that the material is dry and stable before they bag and shrink wrap it and have it sitting in a customer's garden center. And that the spacing of the vapor collection pipes was something that we expected to match their windrow dimensions initially. What we actually learned is there was a ton of energy in these piles, and providing additional oxygen ended up making them even hotter. And we saw vapor coming into our system as high as 170 degrees. That's actually too high, so fortunately we can respond to that to get it into more desirable 160 or below temperatures by increasing the fan speed and lengthening the aeration times. But so far, we've seen that roughly 2/3 of the oil that they used to use to heat the building has been cut back. And perhaps most importantly, we've reduced their time of composting by up to 50%, essentially 4 months down to 2 months. While there wasn't a whole harsh winter, the compost zones that were covered didn't show a big difference during the active phase. However, the piles that are under that covered structure are the ones that are typically dedicated to drying. So if you do get a heavy storm, as you're trying to finish dry a certain product, it doesn't go backwards right at the end. We did need to update some of our condensate traps to prevent water blocks in the lines, but we've been working well for close to a year on that front. And they did have some particular data issues with their own site, but we were able to use a temporary hotspot to still do that data transfer where we could view it. And it's been working great for a number of months now. Just a little more detail on some of those performance observations. Typically in the winter, it might take them 5 to 7 days to get the cold feedstocks up to the 131 Fahrenheit or greater temperatures to meet the process to further reduce pathogens. And with our recirculation and aeration feature, we just typically have been now seeing that in less than 24 hours. So that's a great jump start at the start of their process, and particularly valuable in northern composting conditions. Rather than pulling in 0 or 10 degree air on a cold day, we're able to get the piles started with recovered warm air. Again, we were able to cut the processing time in the active phase approximately in half, and cut the number of turns with that Comtech straddle turner in half as well, typically 14 down to 7. We've got one winter season of the radiant floor, so we'll continue to track the energy consumption. And importantly, the drying process worked very well. This is something that they use quite a bit of propane to dry a couple of their product lines. And now that we're expanding phase 2, additional unit and set of aeration zones, we'll see if we're able to completely eliminate their propane use in their process. Performance otherwise, we've got up to 162 degrees, and not just for standstill water, but be able to maintain that 162 degree water while circulating at 19 gallons per minute in a very cold part of the year. So we're very pleased with that performance. That's the best we've ever done with any of our systems. And part of that, I think, is just because we have the data insights, improved control capabilities, and we're able to dial in the system and help the operator meet their goals. So we're, as I already alluded to, their phase 2 that we're getting close to completing now may eliminate their propane system and primarily use the covered zones for drying. With this phase 2 expansion, we'll have a total of 8 aeration zones. At least 6 will be dedicated to active, and then the other 2 can be used for either active composting or drying as needed. There are images of how the aeration channels are not required to be in pipes above grade. There are some additional slides in an appendix that's going to be in the archive of this webinar that you can see examples of buildings or outdoor pads, either one, that have recessed aeration channels, meaning that they're set down in the pad so there's no risk of the payloader or other equipment hitting those pipes. We've added additional insulation and additional, basically the time and labor and wear benefits is part of why the Fosters were interested to move forward with the phase 2 expansion. The other piece a couple other brief examples of projects that I wanted to share as I wrap up the presentation here. Some people are familiar with rotary composting drums. We developed and have installed a simple heat exchange and aeration unit to tap into the end of it. Had some fun calling it the drum dragon. But basically, we're tapping into the exhaust of those drums and putting that into a hot water recovery system. This project's down in the most southeastern corner of Vermont. The Dunkley family runs Vermont Farm, goes right to the Connecticut River, which borders Connecticut, and right to the Massachusetts border. More or less, this Enviro drum runs their separated manure solids through the drum, a day plus retention time, and it's constantly putting out exhaust vapor at anywhere from 140 to 155 degrees. So our unit is on the left, and we're able to capture that energy from the vapor stream, put it into the hot water loop, and in this case, we have a 400-foot line that runs that hot water to their primary barn, where they have their milk house, sanitation needs, hot water for calves, office heating, baseboard. So it's used for about 5 different applications, and also is saving them some good propane. Our early estimates right now are around $6,000 a year. We'll continue to work with Jeff Dunkley to track his actual utility savings, but he's very pleased with its minimal maintenance and taking advantage of a resource that was just putting a plume of steam out into the air otherwise without our unit. The last example I'll share is our newest project that we've installed this summer in northern Connecticut. well, there's less farms that are still active for dairies. Part of the way that the Collins have diversified their operation, one way, a nice way, is their ice cream stand, but they also have Collins compost. So beyond their dairy farm manure, they take in local leaves and wood chips from landscapers, and also the show bedding from nearby exposition or fairgrounds, the Big E in Springfield, Massachusetts. So they've been composting since the 90s and have a dedicated following of compost end users in their area. They've always used this loader or other equipment shown to turn windrows. So this year, with the support of the Connecticut Farm Energy Program, installed one of our systems, and they have begun aerated composting. Here's a shot of our unit, a hot skid. So being placed on the base of the utility shed that they built around it. Very much the same mechanical components as was shown in the 20-foot shipping container. We just pack it onto a different platform, a metal skid with a frame. Things are a little packed in closer together, but it's pretty handy to be able to move that around in the back of a pickup truck and be able to use forklifts to set it in place. Here's a shot of their aeration pad. So I would call this kind of the lower end of our capital costs for integrating into the infrastructure of a site. These pipes were put out on a gravel pad. As you saw, that block wall being framed around for the outside of a push wall and containment wall. They're interested to build a covered facility with concrete if they can get cost share funding from USDA or other sources over the next couple years. But already they're able to get this into use. Basically in that shed to the right is our equipment that provides the aeration, the draw from all these pipes as it's loaded with the compost. And then the hot water that we recover is sent to their milk parlor for use. So here's a shot of John Collins starting to load some of the batches. And here's a shot later in the summer, essentially run as a 4-batch system. They're able to load different piles at different times. They've gone with anywhere from a 2-week to about a 6-week interval that they'll pull out and reload batches. And we're heading into our first winter season of operation coming up. Couple findings so far. Started up in July. In spite of the relatively low cost infrastructure, they're still able to get temperatures that have peaked as high as 154 degrees Fahrenheit and circulated at 12 gallons per minute. Currently, they did the initial connection into their milk room for sanitation, washing their bulk tank, milking equipment, actually washing the cows before milking. But they have found they've got excess energy that beyond what they're using in the milk house, and will be connecting it into their adjacent equipment shop. And if they find they have enough energy still, it's a couple hundred feet more to John and Ashley's house on the farmstead. And again, just acknowledging Connecticut Farm Energy support, helping bring this to fruition. Thank you all for taking a look at this. Certainly a lot of people have contributed to this project and development of this technology over a number of years. For your reference, there are an addition number of slides that talk about some of the history of how we came to this point in the technology, both individuals as well as other project sites that we've done over the last few years. So thank you very much for your attention, and happy to take any questions via email when you have the opportunity.
What's your maximum length from your heat source to the hot box?
The longest that we've got installed is 400 feet.
Wow.
What we're seeing even on that project is it's about a 1 degree loss from source to the use. We use the same piping that's used in outdoor wood boilers. What they say in the specs is it's about to expect a 0.6 degree of loss every 100 feet. So that's what the manufacturers say. We may see less than that because they're often working with 200 degrees. So there's more potential for heat loss than we're seeing.
Yeah, so it's really not significant.
Yeah, you've got an installed cost of maybe $12 per linear foot, so that adds to your capital cost. The longer you go, but I would think practically for a moderate site, you could go 1,000 feet if the energy use justified that installation cost.
Mm-hmm. And I noticed, I don't know if that's regulatory issue there with the pads that are prepared. Is that required by permit, or is that just done just to make a nice level surface for the project?
Both. So in a commercial or municipal setting, there's often runoff controls that need to be achieved. On the farm sites, then it's just more practical for four-season access of the pad.
Right. What's your payback for a typical project? Do you keep data like that?
Sure. Well, the one I got, Diamond Hill Custom Heifers, comes off without grant funding. That was going to be 4.8. With the grant funding, it was down at like 2.4. So we've certainly got projects that are anywhere from 2 to 5 years of payback. We often do that type of analysis with a customer prior to any purchase or installation. And when the ones that are 2 to 5 are the ones that tend to go forward, and the ones that we've seen more in the 18 to 20 range are the ones that we've got to let go.
That's the long one. Yeah.
Probably the biggest factor is, while we've had interest from like equine or horse farms, oftentimes there's just not enough volume with the equipment that we've developed at this stage to make it cost effective. We'd like to be able to scale down, but with this technology, it's certainly helpful to have bigger, larger compost process. 1,000 cubic yards a year is typically the volume that we'd say is worth us, having a serious discussion and looking into it.
Yeah. How would feedstock impact that? For example, food waste would probably be a higher energy generator, and manures and things like that. Do you factor that into your analysis?
Slightly, yeah. It's the volume is a starting point, and then yes, you'd have more energy in food residuals than you would in a manure. Leaves, however, are actually a great energy source because they've got so much carbon. We find that those batches tend to run hot for longer periods of time than just compost. Yeah.
Well, I guess I've seen food waste. If you put it in a windrow, it disappears within a matter of weeks. So that energy is like a flash in the pan, if you will, versus the long haul with your carboniferous or carbonaceous materials.
Yep.
Interesting. Now, is there a cutoff? Say you have a big picture of the United States. Where this makes sense, this type of project. Is there a cutoffs anywhere? Have you determined that, or are you just kind of saying this is just for the northern parts of the country? I mean, how would this work? I guess it wouldn't work in somewhere like Florida or California.
Well, what I'd say on that is all of our earliest applications of this have been in northern settings, and they were tied into heating barns or greenhouses or processed water. As we've gotten into the product drying, that's an exciting opportunity for us because while I've even use an example, I've been to a compost site that was 400 acres and it was just massive, but they only had a job trailer on the site for a heat load. But now that we're getting into the product drying, any site that has a need to dry the product, particularly coming into spring to accelerate their screening and stabilization for bagging, now we've got an economical use for that material in many more settings. So that would expand to those southern areas that have an abundance of moisture.
Right. Yeah, I mean that you could apply that to grains and stuff like that, you know, from a farm. You know,
Absolutely, and dairies are doing that with well, the Fosters, in fact, did that with green sawdust. So they were able to essentially get sawdust down to the same moisture as kiln dried sawdust for animal.
That's neat.
So yeah, we're excited about that expanded application.
What was the other question I had? Oh, that last example you mentioned, was that a static pile or was that a turn pile system? That one.
So it's primarily static. So any of the turning that they would do would be a single flip from side to side.
Right.
What they would like to do, as I mentioned, is be able to harden this facility a little more with a concrete floor, put in the recessed channels, put in a coverall or other type of structure, and that would allow them much easier flipping or turning from side to side. So this, while it really accelerates the early stages of active composting, you're still going to have an outer crust that you're going to want to physically handle if you're going to be using this material for a retail product. If it's being used exclusively for a coarse bulk compost or for ag application, that may not be necessary. So that's entirely determined by your targeted end use of the compost. I just want to acknowledge here on this slide here, Jim Foster Jr. passed away this year, and he was the primary site operator at the Fosters, and just want to acknowledge what a great person he was, and certainly a composter of note. And that was just last month, so in a farm accident. So that was a sad thing, and certainly just want to give him an acknowledgement. All right, well, going into the background of history of composting and heat recovery, while we're really proud of what we've done, we've certainly learned a lot from some other sharp people and always learning from our customers. The idea of these slides is just, while some people may have a concept of the composting and decomposition process releasing heat, these temperatures of 155 up to 160 are fairly common on medium and large size compost operations. It's not necessarily what you'll see in your backyard bin, but you can see the steam coming out of piles when it's turned, even in March, or snow-covered piles in the background. So you give those microbes the right food, moisture, and air, and they're going to go to work and start releasing a lot of energy as one of the co-products of this process. This has been known to some degree for thousands of years, and there's at least anecdotal reports of the Chinese, the French, and others doing this with garbage heaps or compost heap under gold glass houses. As agriculture modernized and solid waste handling modernized, some of these old practices went away, but in some way we're looping back to that, and we're trying to optimize it, particularly with aeration systems as our means of facilitating the energy transfer. Jean Pain is when people talk about compost heat recovery, he was this French-Belgian farmer who developed these mounds, largely of wood chips and forest products, but he would physically coil pipes through the process. So this, again, is what informs a lot of our work, but we do not put pipes in the piles. So this is an often education process that we share with people, that no, we don't have pipes in the piles. That would not be practical at any large scale farm or commercial municipal compost operation. But we do benefit from his ideas. Agrilab, who I mentioned before, kind of the creators of some of the proprietary and patented aspects of the heat transfer technology, are in Windsor, Ontario, right across from Detroit. And in this relatively commercial urban area, they did a pilot project to test their early systems using composted manure bedding and spoiled feed. Based on that, they started marketing these products, and that's how I actually heard of them and helped bring them into the project in northern Vermont at Diamond Hill Custom Heifers. Again, Agrilab still active in a lot of industrial aerospace, oil and gas applications, and they helped us and licensed us the technology to start a Vermont-based company. City Soil and Greenhouse, the other company to draw attention to, Bruce Fulford in particular, he's been doing these compost heated greenhouses on and off through his career, going back to the New Alchemy Institute Revision House, and now he's the contracted operator for the Public Works Department in Boston for all their municipal leaves. Here's some drawings of some of the early systems that he developed, and Bruce has been a great social activist as well, getting urban agriculture projects initiated, working with this community in kind of the Jamaica Plain, Mattapan part of Boston. These next slides are of different projects that we installed in Vermont and elsewhere in the Northeast. All our early projects were on farms. This project and farm is owned by Terry and Joanne Magden. They're only about 8 miles south of the Quebec border, so things get cold. And as they were building a new calf barn, they wanted to develop a system where they could recover the heat. And I was able to come in and be part of the project to help make that happen. Pointing out that while a lot of manure these days is managed as a liquid, they had a lot of solid manure raising the calves and young stock. So having that solid feedstocks is important to identifying good compost sites. There is mechanical dewatering equipment, and I believe Brett Reinhold, they have a separator at their farm that does that, recovers the fiber from the liquids, but having the solids is important. Here's some construction shots of how the piping was laid down into the floor with insulation, and then this was cast into a concrete slab. The holes in the wall that these pipes are connected to go back into this mechanical utility room. Again, this is our earliest system back in 2006. This went online, but we used a lot of commonly available materials, very much a kind of Yankee farm creation. But the manifolds would draw the vapor in, and then the fans would push it up into the ductwork. Within that ductwork, these are some of our other heat exchangers that we've used, kind of a more longer linear approach, but they would be able to transfer the energy in the compost to a hot water tank that was then able to be circulated to a number of different zones, heating floors, different parts of the barn and calf facility, as well as also for using as wash water and heating water to make the formula, the milk replacers for the calves. As the system was fully installed, here's a view of compost batches being loaded onto the aeration floor. They enclosed this composting floor within a metal-sided pole barn, just to point out that the lines are aeration channels that are set into the floor with cover plates. And you can see a layer of lighter material below the darker mix of manure compost. Those are wood chips at the base, again, intended to help spread airflow at the base of the pile and prevent the particles of the compost mix from plugging the aeration ports. Actually, there's Joe Ouellette, the patent creator, gentleman from Canada, when we were down at Sean and Sandy Quinn's farm in New York State. They put in a similar system on their farm within a coverall structure. On the other side of the working floor is their aeration ducts. Insulation is important to maximize the amount of heat that we can recover. Here's another example of a farm in northeastern Vermont, Jasper Hill Farm. They're a small dairy and cheese maker. If you have not tried Jasper Hill cheese, you should. It's outstanding. It's won a national and international awards. The red building to the right in this picture is a combined manure handling facility and greenhouse. So there's composting bays, on the dairy barn side of this building. They've got small digestion tanks, kind of visible through the door, and then a greenhouse portion of the building facing to the south and east. Really cool operation all the way around, and they installed another one of our early systems. So we'd aerate the compost piles and then would recover it through a system to use to heat the greenhouse and also maintain temperatures in their biogas digesters. I won't show the video now, but this video is available. This and a couple other videos are available on our website to further explain the process. This is our project that we have done in New Hampshire. It's at the University of New Hampshire, and they have a second dairy farm as part of their university that's focused on organic dairy research. They've got a small milking herd, and they have bedded pack housing, which means that they don't have a liquid manure, but they accumulate all their manure on top of bedding through the course of the winter season when they're not on pasture as much. But they've been great partners in terms of studying the energy dynamics of this process. They're making compost, I want to say, for $4 a yard of inputs. So it's very economical compared to some of the other manure handling strategies. And then they also are tracking through SARE, Sustainable Ag Research and Education, the various carbon, nitrogen, and other nutrient and energy flows, both on the farmstead as well as throughout their farm. So I encourage you to check out the work of Doctors Matt Smith and John Aber and Allie Leach. They're also looking at the greenhouse gas implications of this, as we know manure can generate methane, as can food scraps and landfills. By aerating the compost, they're finding that they can virtually eliminate the methane emissions from these piles. So they hope to be developing a protocol where this approach to aerated composting can also be eligible for greenhouse gas reduction credits. A couple shots of their construction process. They also used a concrete aerated floor with inset channels and all the ductwork in their utility room next to the aeration and heat recovery unit. There's Dr. Matt Smith. We got to work with him as he worked through his graduate work and is now a PhD. But again, excellent partner, and perhaps some of you have met him at composting conferences over the last several years. He's fortunate to still be working with the university in a postdoc position, so you can still contact him for his findings. Shot here of Gene Bonatal visiting our site when we did a temporary system at Vermont Compost Company. Very cool site. They not only do a lot of composting for a number of years of food scraps and other local resources, but they feed as much as the food scraps as they can to a flock of chickens, and do not feed these chickens any grain, and are, at one time at least, were the 4th or 5th largest egg producer in the whole state. So just very interesting holistic operation. Gene came up from Cornell to check out our work. You can see in this picture here, we put the mechanical equipment into a mobile cargo trailer, and we did some temporary piles below their product testing greenhouse. Vermont Compost Company sells high-end soil blends from compost that are in demand in the organic growing market, and they do a lot of product testing to make sure that they have maintained good plant growth conditions. So just a shot of how that project was set up, heated their greenhouse, schematic of the flows, again, pulling the air in from the compost, running it through the heat exchanger, directing that hot water up to the greenhouse for heating the building, as well as for tempered irrigation water. And Carl Hammer, their longtime owner-operator, would do tomatoes, peppers, other things that prefer to have warm water rather than being shocked by cold well water. Some of our earlier remote tracking that we were able to track the trends. We've refined this further since then in the last several years. A couple other projects to close out with, the compost heated greenhouse in Boston. We got to work with Bruce Fulford, who I mentioned earlier. Beyond composting the leaf and yard trimmings from the municipal sources, they developed an urban agriculture portion of the site and created a number of gardens and a greenhouse that was entirely heated by compost. They dubbed it the Mattapan Ecovation Center. It actually was awarded the Greenovate Boston recognition last year for sustainable agriculture, and they've brought a lot of people in from their local community. Their primary inputs are bagged and loose leaves. The city has approached them to start taking in food scraps as well. That has not happened yet, but we hope it can. And these next few slides that again will be on the archive show how we were able to bring in on short notice a unit that was needed to be temporary to abide by their contract, but they cleared the site, built a greenhouse using jersey barriers, did aeration, did trenches for us to set the aeration pipe, connected to our unit, the aeration and heat recovery, data and controls, and then built a greenhouse over it. The north end of the greenhouse had 3 aeration bays, and the south end of the greenhouse was growing space with an odor biofilter. So beyond recovering the hot water, they also scrubbed and recovered some residual thermal energy through these raised growing beds. Fascinating project, and in the about a year and a half that we had our equipment down there, they cycled through something like 10 different rotations of food and ornamental crops. Just it was a pleasure to work on that project, and we've been working with them on a couple projects to deploy this on a larger scale at the nearby Parks Department and a couple other facilities in this part of Boston. Here's a view inside of our trailer. Again, the aeration, heat recovery equipment, circulator pumps, hot water storage, tracking with both manual gauges and the data that we can remotely view and access from our offices in Vermont to support the project. But again, this was part of what we did. We were part of our part of the project, but Bruce and team really brought together a whole community here. And this was the hot skid equipment. This is ultimately the unit that was deployed at Collins and is sent off. Also have one of these in Wales. Thought there was a nice picture of fall foliage to end the presentation on. So thank you very much for your interest.